right, Math 5130, extremely important video. So slow down, do your best to focus, and write this down in your notes. I'm going to share with you some vocabulary. Build on just a standard one sample T or Z test, and build the foundation for future lessons. So um, first thing I think about is, again, I'm trying to prepare you for your capstone project in your program, where most of you or many of you will uh, come up with something to test. You'll collect your data, you'll analyze it, and you'll maybe even publish. So the 5 stages is: we generate a research question. I like to think of those as pretty much you observe the world around you, and you're just curious about certain relationships. For example, since COVID, there's been a lot of shift, a lot more attention to delivering instruction online versus face to face. And I'm one who's interested in this, and I kind of wonder, is the face to face, or I should say, is the online instruction as effective as face to face? And the answer to that's not going to be a simple yes or no. The more complex the issues, the more complex, obviously, the answers. So next thing I'd want to do is, we just can't throw stuff at the wall and hope something sticks. If we generate a research question, we need to have a theory that kind of explains the initial observation. And what I would think there is, we're all at this stage very dependent, addicted to technology, our phones. And I get that annoying, you have been on your phone for, however many hours per day. I think I get that every Sunday. In fact, I usually get it when I'm in church, which is weird. But not sure what the message is there. But, we spend a lot of time. I spend a lot of time on the computer. So I'm comfortable learning. For example, again, I am creating this video in November of 2023, and we have, a war in the Middle East between Israel and Palestine. And the other day, I wanted to learn more about the history of the relations between the two. And so, I went to technology and Googled it and found a really cool article by NPR. So anyway, my theory that would generate, kind of motivate the research question would be, we do seem to be becoming more and more comfortable learning with the use of technology, and we're not even going to get into artificial intelligence, but and ChatGPT and all that stuff. Number 3, break it down into a theory and just set a testable predictions. I believe that for most students, face-to-face, or I'm sorry, online instruction is as effective as face-to-face instruction. And you hear a lot of people, well, I don't believe it because my daughter took a class in school and it was online. She couldn't learn anything. Well, the world doesn't revolve around your daughter. Our world revolves around our kids. But making broad statements about the effectiveness of instructional techniques doesn't revolve around the experience of one single person. It's the reason we would never, ever go out and conduct a study based on one person, unless you're doing some sort of qualitative study or something like that. But statistically, quantitatively, you would never do that. So 4th step, collect your data to test your theory. 5th, you analyze your data. And that's kind of where I come in. That's the part that I'm trying to help you in this class, is learning to, once you generate a research question and collect your data, how do you analyze the data? So again, I'm going to be jumping around here, but a lot of important stuff. Why do we use 0.05? That's one of the first questions that I asked myself when I first started getting serious about studying statistics. Why not 0.02? Why not 0.07? Why not 0.10? But just for the sake of being on the record, 0.05 is the industry standard, as is 95% for the level of confidence. You kind of wonder, wait a minute, 0.05 plus 0.95 adds up to 1. Is there any relation there? Absolutely. For example, if I was for some reason going to calculate a confidence interval with 99%, then I would use an alpha value of 0.01. So I went back in the literature. No one really seems to know why we use 0.05. A lot of people kind of hypothesize, make an educated guess that it goes back to the early days in banking where financial institutions were able to withstand a 5% error when lending money. Now, what does that mean? You think about lending money, the bank's going to take your application, examine your profile, and decide whether or not they're going to lend you the money. So they're either going to lend you the money or they're not. And the outcomes, possible outcomes there, the customer will pay back the loan or they won't pay back the loan. So if the bank lends the money and the customer pays back the loan, then that was a good banking decision. If the bank decides not to lend the money and it turns out that the customer wouldn't have paid back the loan, then that too is a good decision for the bank. I think the interesting part comes in the errors, and the errors would be that the bank lends the money, the customer doesn't pay back the loan, or the bank doesn't lend the money when the customer could have paid and would have paid back the loan. So those are errors. And the best that I can determine is the 5% error rate comes from banks lending the money and customers not paying back the loan. They were able to withstand a 5% error rate for that box. So I think that's the research I can find where 0.05 comes from. Now that makes a really, really good transition into statistical errors. And we have two types of statistical errors, a type 1 error and a type 2 error. Now we think about from a standpoint of the null hypothesis. The null hypothesis is either true or false. We as researchers never know if it's true or false because the statement is about a population. And we can't go out typically unless we conduct a census. But typically the way inferential statistics works is we base our decision on a population value based on sample data. Well, sometimes we get sample data that's representative of a population and we make correct decisions. And sometimes we go out and get a sample data that's not representative and we make errors. The almost goofy part of this is we never know in practice if we've committed an error because everything is based on probability. So we can look at this box. It gives us a lot of good definitions. For example, the definition of a type 1 error, which is the top left box, is when the null hypothesis is true and we reject it. So a type 1 error is rejecting a true null hypothesis. If a null is true, we don't want to reject it. We want to keep it around. A type 2 error, which is in the bottom right box, is when we fail to reject a false null. Well, if we make a false statement, for example, we say that the mean hospital charge is $20,000, and if that's not true, then we want to reject that. If it's not true, we want to find out what it is in the world of statistics and decision making. So that is a type 2 error. So again, type 1, rejecting a true null. Type 2, rejecting a false null. Now, alpha is the probability of committing a type 1 error. So when we set alpha at 0.05, we are allowing ourselves a 0.05 probability of rejecting a true null hypothesis. Beta is the probability of committing a type 2 error, and power, which is just 1 minus beta, is the probability of rejecting a false null. The goal in any study is to reject a false null hypothesis. So that is defined as our statistical power. So take a screenshot, tattoo these to the brain because they do come up from time to time, especially type 1, type 2 errors, alpha and power. The power is a function of beta, so there we are. So alpha, again, the probability of committing a type 1 error. Common choices for alpha are 0.001, 0.01, and 0.05. Beta is a function of alpha. We don't calculate beta in the real world. So if you think about it, alpha versus beta, if we set alpha at 0.001, we will very rarely commit a type 1 error. If we set alpha at 0.01, we rarely, only 1 out of 100 times. If we set alpha at 0.05, not likely, 1 out of every 20 times. And if we set alpha 0.10, 1 out of 10 times, we'll commit a type 1 error. Now, I think inquiring minds at this stage would say, well, if alpha, we don't, okay, errors are bad. And at 0.001, we very rarely commit one, then why wouldn't we always set alpha at 0.001? Well, the reason is type 1 and type 2 errors work inversely. As our type 1 error goes down, the type 2 error goes up. So when I set alpha at 0.001, I'm not going to commit many type 1 errors. Only 1 out of 1,000 times that I conduct that study. But I open the door for a type 2 error being, quite likely, actually somewhat likely. As I increase the level of alpha, notice that the type 2 error rate decreases. So again, these things work in kind of combination with one another. As one goes up, the other goes down. So I think it's safe to say that statistically, statisticians or 0.05 has become the industry standard because it's just kind of a middle ground for controlling type 1 and type 2 error rates equivalently. So again, this screen just puts into just types out what I've just told you. So a couple of things to note there. Desired level of power is usually 0.80. So again, power is the probability of rejecting a false null. So we want a high probability. But if we get too high probability, then we get into this practical versus statistical significance issue, which will come up later. Now, let's switch gears to effect size. Just because a test statistic is significant doesn't mean that the effect it measures is meaningful or important. So the effect size gives us another measure of the strength of the relationship. Now, here's what happens. For statistical significance, for example, I can raise my sample size, and there's no better way to raise power than to raise sample size. Well, if I just keep raising sample size and raising it, pretty soon I'll get a power that's so high that I just am going to always get statistical significance. But it doesn't mean that there's really a true relationship between the variables that I'm studying. So, a few things about effect size. They're standardized. They're easy to find. You can get on Google and type, effect size for ANOVA, effect size for regression. That's what I do. I don't have any of this stuff tattooed to the brain like I do all this other stuff that I teach you. There are many different types of effect sizes. For example, for a t-test, a one-sample t-test, there's I can sit here right now and think of 5 of them, and I'm sure there are probably more than that. Cohen's-d probably is the most common for this, and that's a situation where when you're conducting your study, and maybe you're using a statistical technique that isn't covered in this class, you reach out to someone like me and say, hey, I'm working mixed models. What effect size is appropriate? if you can't find it through a Google search. So effect size, for example, for a one sample t-test is just found very easy. Just take the sample mean minus the population mean and divide by the standard deviation. And then we use the Cohen-D metric. So any Cohen-D from 0.2 to 0.49, we would report as a small effect size. Any effects, Cohen-D 0.80 and above, not to be confused with the 0.80 for power, two different things. It just so happens that the metric for Cohen's D is 0.80 and higher for a large effect. Now, if we circle back to the t-test that we conducted a few videos ago, where we tested that the mean charge for delivery was $20,000. Cohen's D, take the sample mean, 15,478 minus 20,000, divided by the standard deviation, which was 47,696.54. And I get negative 0.095. We always take the absolute value of effect size. Effect sizes are never negative. So I would report Cohen's D at 0.095. Circling back to the magnitude scale, notice that 0.095 isn't even large enough to make it on the scale. So we would report that we have a very low effect size. And the reason is this is a really strange distribution. You would really, if you remember, I had a lot of outliers. It was severely positively skewed. One of the assumptions for a t-test is we have normality. You can't convince me that this sample data came from a normal distribution. So we have some real nuances with this data set. But again, for illustration of a t-test, I think it was just fine. But there would be a very low effect size. And the reason is because our distribution was quite wacky. Statistical power. Power of the test is the probability that a given test will detect a difference if it exists. And again, it's the probability of rejecting a false null. I can almost guarantee you that's going to be a test question on your first exam. And we aim for a priori and an achieved observed power of 0.80. So speaking of priori power, that's a power analysis that we run before we conduct our study, before we even collect our data. So what we can do is we can use a fancy statistical software package called G-Power. I'll demonstrate that later in another video. And we'll put in all the parameters of our problem and put in a power of 0.80 that we seek to find, and then it'll, the software package will tell us the sample size that we need to achieve that particular level of power. Now, we go out and we do our best to collect our data with that sample size, and then we come back and analyze our data, and we'll have missing data. In the real world, data collection isn't perfect. I've seen situations where I'll start out with 300 participants, and by the time I cleanse the data, I'm down to 150. Well, if 300 was our desired sample size to achieve a power of 0.80, then by the time I cleanse my data and quite possibly limit the sample size, then my achieved power is going to go down. So because of that, when we're analyzing our data for each statistical software or each statistical test, we will report the achieved power. All right, gang, I know this is probably making your head spin, giving you a headache probably, but again, I just want this on your radar because this stuff is going to come up as we get to more sophisticated types of statistical techniques. All right, have a great day.